Let me share the screen. So before we go further, a couple of questions from the chat. Grid.sync doesn't seem to be working for all of you, and there is a reason behind that, right? So even if you implement your own global synchronization, what happens is that there is a notion of something called as resident blocks, which means that on an SM, when we assign multiple thread blocks, not all of them are running at the same time, right? And some of them might be still yet to be taken for execution. Now, if there is a global barrier which requires everybody to reach that point, the thread blocks which are running are kind of waiting for the non-resident thread blocks to reach that point, but they are never taken for execution. Right? So this creates a problem, and in fact, your code might hang. If the code doesn't hang and somehow it goes ahead, it might not give the correct answer, right? Depending upon the implementation. So this is a problem, and one of the solutions to this is to have the number of blocks equal to the resident blocks, number of resident blocks supported on that hardware. That is precisely decided by the number of SMs, right? So if you have number of blocks equal to number of SMs, then there is no problem. But as soon as it goes more than that, then it's not clear whether it will always work. So, however, if you reduce the number of thread blocks to a very small number, then number of SMs will probably be some 50, 60. So if you reduce the number of thread blocks to that, then we need to process multiple elements per thread, and that increases the sequentiality of thread processing, which affects performance, but hopefully the correctness is retained. So that is one reason why many of the global synchronizations as well as grid.sync might not work. The second question was about the RDC equal to true, and what does that mean? So this is just a compiler flag which indicates that generate the relocatable code, right? So by default, the code that gets generated from this command line, it appears that it will not be relocatable. But in some cases, for example, dynamic parallelism, right, where we can launch a kernel from a kernel. So we can launch a kernel from a kernel. We can do recursion also. So that requires that the code should be possible to be put at different places in the memory. So by default, if it is not relocatable, then this will not be supported. The dynamic parallelism recursion or getting called from multiple places or repeatedly, that will not be supported. So therefore, that RDC equal to true is required in such cases. I don't know why it is required in grid.sync, but definitely for dynamic parallelism it is required. But should not this be taken care automatically by NVIDIA architecture? Soumik says that upon a grid sync, all the blocks should be executed completely, even by context switching among the blocks. Yeah, ideally, yes. Even in this case, unfortunately, what happens is that the number of thread blocks is decided by the programmer. And I think, yeah, so I'm not sure. I agree with you, but yeah, I don't know why this decision was taken in this manner. Right? Is there anyone for whom grid.sync is working without any problems, even for large inputs? That is large number of thread blocks. Okay, maybe some others may not have tried. Okay, sure. So I'm not sure why this decision has been made, but looks like, yeah. Okay. There is another question by Darpan. What's the difference between grid.sync and sync threads? Sync threads is for 1024 threads or less within a thread block, whereas grid.sync is, it works across all the threads on the chip. All right. So feel free to ask more questions. Meanwhile, I'll start today's topic, which is essentially CUDA topics. So we are going to look at 2 or 3, depending upon the amount of time we have. interesting topics in CUDA, right? So the first one is related to functions and a library called thrust. So we said that there are functions possible even on the GPU. So far, whatever we have done, there is main and then there is a kernel, right? So that is what we have been dealing with. And we know that on CPU you can have functions, but on GPU also we can have functions. Those are decided by __device __ mnemonic. Such functions are executed on the device, that is on the GPU, and also callable from the device. These cannot be called from the host. If one needs to be called from the host, then that needs to be a global, that is a kernel. At the same time, the kernels are also callable from the device, and that is where I was mentioning that dynamic parallelism is possible. I mean, that part is called as dynamic parallelism. So what that means is that you can call a kernel itself, or from one kernel you can call another kernel. In addition, there is a host keyword, which essentially means that it's a CPU function. Can somebody tell me why do you require a host function? I mean, host mnemonic. I mean, if you don't specify, then by default anything is a host function, right? It's a CPU function. That is what happens in C. So for example, main we don't declare as __ host __ So can somebody think of why would that be specified? Okay, so we'll probably come back to this question and we'll probably understand it from the example. Okay, so what I'm giving you is one example. Some optimizations are only for GPU. That is true, but then even if you don't specify __ host, it essentially indicates that it's a CPU function. So we could find that out, isn't it, Chinmay? So the answer is given in this, that some functions can be marked as both host entities. Okay. And for that, we require that host to be explicitly specified. And such functions can run on both CPU and GPU, but of course, the onus is on the programmer to ensure that the code within that works on both CPU and GPU. For example, if you are using printf, that works on CPU as well as GPU, so that will work. But let's say that you put threadidx.x, that works only on the GPU and does not work on the CPU, so the compiler will give error. Or in contrast, if you give, let's say, string copy function, that works on the GPU, but CPU, but not available on the GPU, so again the compiler will give. Okay, Soumik says, isn't host device equal to global? You tell me, will that be? Global is the entry point into the GPU. Right? So whereas host device essentially are auxiliary functions, which of course from the CPU you can call, but from the kernel also you can call, but there is no switch that is well. In case of global, how should I put it? Okay, let me put it this way. In case of calling a device function, we don't need to specify the launch configuration or parameters, because device function is a function which is going to get called from every thread separately. Right? Whereas a kernel requires a launch configuration. Right? So because the device function, when it gets called, since each thread is calling it, it's already parallel. Whereas the kernel is not already parallel. It needs to be made parallel by specifying the launch configuration. Right? So for calling a device function, we don't need to specify this. As an example here, dhfun from okay, let's talk about first device, right? So there is a device function, dfun, right? That takes some parameters. So the syntax is quite similar to a kernel, except for this __ device. But when I call it from a kernel, right? So I don't need to specify any launch configuration, because this particular kernel is already parallel. So each thread is executing this code. So each thread essentially calls this function. Okay, so that is how we should view this. In a similar manner, the host is anyway sequential. So therefore, when you call a host function, that is again going to be sequentially executed by that particular call. Right? So it's more like a jump instruction which starts executing. Okay, so that sounds fine. Yeah, the overall program is split across two slides. So our main can call dkernel, and main can call the host function also, and main can call the device host function also. Okay. So if I want to show it pictorially, it looks like this. So there is main. So this part, upper part is CPU, lower part is GPU. Main can call host function, main can call a kernel, and main can also call a device host function. Right. Similarly, host function can call dhfun, but host function cannot call dfun. Right. So that is one difference. Kernel can call dfun, and dfun can call dhfun. Can dkernel call dhfun? Can dkernel call dhfun? Okay, Sandeep says yes. Satyabhagan says yes, I think. Chinmay says yes. Soumik says yes. So that's right. So yeah, Binong says yes. So the dkernel can call dhfun because yeah, with the same facility as given for dfun. Right. So something running on the GPU can call dfun. Similarly, something running on CPU can call dhfun. Can you tell me what are the other arrows possible in this diagram? I mean, although we have not coded it up, but what are the other arrows possible in this diagram? Like we said, dkernel to dhfun is possible, right? So that is one. Host function calling dkernel, that is correct, right? So host function can call dkernel. So it is possible to have this arrow. It's possible to have this arrow as well, as we discussed. What else? Main to dfun. Okay, so that is not possible. Right? So because dfun is not callable from the host, only a kernel is callable from the host, and dfun is only a device function. So that is not callable from the main. Okay. Any other? Okay, so there are these recursions also possible. For example, main can call itself, host fun can call itself, dkernel can call itself, dfun can call itself, and dhfun can call itself as well. Right. So all these self arrows are also possible. Now you have to tell me if dfun to dkernel is possible. Can dfun call dkernel? Okay, I'll come to Soumik's question also. Can dfun call dkernel? Sandeep says no. Soumik says no. Okay. Okay. So it turns out that it is possible. Right. So from dfun we can call dkernel. Right. So that is essentially the dynamic parallelism part. So like from dkernel we can call dkernel or any other kernel. Then its context, I mean that particular thread which is going to be dfun can also call another kernel. Right. So that is possible. So this arrow is also possible. With thread size specified, yes, that's correct. I mean, we'll have to specify the launch configuration. Similar to exactly how we launch it from the host, we can launch it from the dfun or dkernel. another kernel or the same kernel. Okay, let's come back to Soumik's question. Right? Can DH1 call host? Any suggestions? Okay, now Sandeep and Bhagavan are saying yes. Possible when it runs on host, Sayan says, Soumya says yes. Okay. Okay, so can DH1 call host1? The answer is in general, no. The reason being that DH1 is supposed to be having a code which should be runnable on both host and device. DH1 should have code which is runnable on both host and device. And therefore, anything which is callable from DH1 should also satisfy. Right? So if host1 contains some code which is specific to the host, then that is disallowed. But there is a small exception to that, which I'll mention later with an example. Therefore, DH1 calling host1 is in general not allowed. And for the same reason, DH1 calling dfun is also not allowed, because that becomes a device only code. So always remember that the DH1, once you reach DH1, everything should be runnable on host and device. Right? So therefore, any call from DH1 has to happen to device host function. It cannot be device only function or host only. Okay, sounds good. And therefore,
sir, I have a doubt. With this DH1 can be run on CPU and GPU. So already you have said this is a serialization only. Parallelism is not possible, right?
Sorry, I didn't understand that. Serialization and?
This is a parallelism is possible in DH1? No, because it is running on CPU also. So what is the usage this run on GPU?
Right. So the usage of dfun is going to be translated to the usage of DH1 also. So dfun is also sequential. It's just a device function which is being called from every thread. So the parallelism lies in the kernel, right? Because the kernel is being executed by multiple threads. Now each of these threads is calling their own dfuns. In a similar manner, each of these threads can call DH1. So DH1 is not parallel. It depends upon the caller. If the caller is CPU, it's sequential. If caller is a kernel, then it is going to be parallel. I mean, those many copies of DH1 will be run. Is that reasonable, Puraj?
Yes, it's okay. Okay, thanks.
Okay. So we'll look at one good example of this. Although whatever example I had shown here, that is something which will work in the sense that since there is only printf, but will require both of these host and device further. But I hope the main idea is clear, that if what kind of functions are callable from what type. If there are any questions, please feel free to ask. Okay. So yeah, so that DH1 to dfun, it's not possible. Okay. We are going to study something called, since this is a bridge course, I didn't talk about the host unlocked memory, but let me introduce that here. So some of you were asking when we were saying that CPUs and GPUs have different memories, right? So some of you are asking, isn't there any shared memory between that? So there is no hardware shared memory in that, but there is a mechanism provided in CUDA which allows you to have a memory which appears shared between CPU and GPU. That memory is called as pinned memory or host unlocked memory. And what that means is that you can create, or in some sense malloc, a variable in this host unlocked memory, and then you can access that variable from both CPU and GPU. Okay, and the effect is such that whatever you write from the CPU side, that is accessible or available on the GPU side and vice versa. Okay, so let me show that with an example. But in additional, what I would say is that because now this data is accessible from both host and device, you can have a control or a code which can run on both CPU and GPU. If that accesses this host or lock memory, then your code will work on both CPU and GPU. Right? So the memory that you use should be accessible from both the devices. So therefore, host device functions and the host or lock memory, the control and the data, which are kind of what you say, working on both the devices, are going to be friends of each other. Right? So let's look at a code for the syntax of host or lock. So I declare a pointer, and then I do a CUDA host or lock on that pointer with the appropriate size. It could be an array also, doesn't matter. And there are some flags which indicate that, you can ignore those flags. Now, in the next statement, I do star counter equal to 0 from the CPU. Okay, and I print it from the CPU. I can pass that as a parameter to a kernel directly. Right? There is no CUDA malloc. Right? Star counter was CUDA host lock, and I used it on the host. I pass it as a pointer to print K, and directly I use it here. Right? I'm using it in fun, but you can also use it in the same function. And after that, I have CUDA device synchronize, and then there is fun counter again called from here, because fun is both host and device. It is callable from both the device as well as the host. Okay, and then I print the value. So now you can see by looking at this code that that counter variable is almost like shared between CPU and GPU, but that doesn't mean that there is actual physical memory. It gets actually CUDA mem copied from CPU to GPU and GPU to CPU every time. Sham says, is there a size limitation for the host or lock memory? Yes. Well, yes, in the sense, not at the programmable level, but the operating system might have a limit. And the reason being that this uses pinned memory. So pinned memory meaning that usually our pages are swappable, right? So we use virtual memory. So it's split into these pages. And whenever you are not using a page, that page can be swapped out to the disk. By pinning that page, the operating system ensures that that page is always resident or visible, accessible. So it gets implemented that way, right? So if we use a few pages of pinned memory, it is okay. It doesn't hurt performance. But as soon as we start using too many pages, it's now reducing the number of pages accessible to the operating system to perform the swapping. And therefore, the performance of the operating system reduces, and accordingly, the performance of the applications also reduces if we use too many pages. Therefore, the expectation is that this pinned memory or host or lock memory should be used to maintain some metadata rather than maintaining some data. Right? For example, the diff in your page rank can be stored as a host or lock variable. Soumik says, is it passed based on page fault? No, it is not passed as a based on page fault because it is pinned. It actually gets, the page fault doesn't occur. However, there are, okay, so at the basic level, we should view it as whenever you write from one device, the other device gets a CUDA mem copied value. But there are optimizations done on this where you don't need to copy every time. You just need to copy when the other device needs it, right? So those are also done. The one that you are talking about as page fault is not this pinned memory, but there is something called as a unified virtual memory, which is also supported in CUDA much later than when pinned memory was supported. That uses page fault mechanism to ensure that whenever there is a page fault, that means that it is not available on this device. Let it be copied from the other device. So that uses pinned memory, that uses page fault mechanism, but not the host or lock memory. Soumya Lakshmi says, every time a change happens to the variable, it is passed from GPU to CPU and CPU to GPU, or only when the function ends. It is passed every time is what we should imagine, the problem is the same as happens in multiple threads when we said that there could be cached copies, right? So when I write from one variable, one device, one thread, it's not immediately accessible to the other thread unless I have a barrier or a thread fence and the other one uses volatile, right? So exactly in a similar manner, there is a weak consistency across these devices where if you write from one device, it might not be immediately copied. Right? It is eventually going to be available to the other device, right? That is what the documentation is going to give guarantees on. Except when you have a barrier across CPU and GPU. And what is the barrier across CPU and GPU? Is there a barrier we are aware of between CPU and GPU? Kernel invocation, okay. CUDA device synchronize global barrier, right? Okay. So I was talking about CUDA device synchronize. Kernel invocation is definitely something which at the end has a barrier. And the global barrier that we discussed was primarily across threads on the GPU. But CUDA device synchronize is a barrier across the two devices, host and CPU, host and GPU. Right. So if you have a CUDA device synchronize, and after these writings from the CPU and GPU, then it ensures that the data is copied across the or synced across the two devices. Okay, so only that guarantee it can give. Right? Beyond that, it is eventual consistency kind of, in the sense that eventually the data is going to be available. Another question from Abhishek is, are pin pages cached? I think pin pages do get cached. Will it cause any problem? Do you foresee any issues with that?
I mean, since these are pinged, so all the transaction on that memory should be at a single place. So if they are spread out across hierarchies, then again we'll have to have some coherence across these levels, and so that is why I was asking.
Yeah, so the pin memory gets used exactly similar to the rest of the global memory. So there will be these coherence issues that will come up with respect to pin memory also. Right, so the pin memory is not solving that problem. So which means that if it can cache the data, and the application might use the cache data, and that means that it might not even get updated in the pin memory, right, let alone on the GPU. Right, so that is all possible, and that is where this weak consistency part comes into picture. Okay.
So, but I mean, in a sense, your original CPU might not be using weak consistency, but these pin pages somehow add create that doubt in the CPU's consistency model, right? Because our CPUs are mostly have order on writes, total store order, but these pin pages might add that extra weakness in the ordering of writes to this pinned locations.
That is correct. So these pin pages will add extra some sort of inconsistent behavior, but that will not change the total store order possible. It will still remain within the TSO order. So what I'm trying to say is that you are increasing one level of the cache, but that doesn't mean that you are creating a problem with respect to changing the consistency.
Okay, sir.
Okay, so sounds good. So I hope this point is clear, that host device functions are runnable on both host and device, and therefore having a data which is accessible from both host and device is going to be very helpful, and something which actually gets used in thrust later, and therefore we should be aware of these things. Okay. So okay, by the way, what is the output of this code? Any suggestions? Okay, let's discuss that, right? So we are going to print 0 here, then print k counter happens, and there is global synchronization between the two devices, and therefore this print should complete. So fun counter, so that increases to 1. And so printf after fun prints 1. After that, fun counter gets called from the CPU, which increments the same counter, and from 1 it becomes 2. So main after fun becomes 2. Okay, so that is the expected answer. Okay, so can somebody tell me what is the output of this code? So the most of the code remains the same as we had earlier. I have just changed this fun function. Anyone? Okay, so it turns out that this code will not give any output because this code doesn't compile. Right? And you might be wondering exactly that why am I asking about this output when the code itself doesn't compile? Because the code doesn't compile because deadlock if we wait for a call from main. Okay, right. So as Sandeep and Vipin have suggested, host cannot do sync threads. It's supported only on the GPU. Right? Therefore, the host function, since the function fun is host device, it must have code which works on both host and device. So sync threads is not supported. Okay. So how about this? That instead of doing host alloc, if I do a CUDA malloc, how does the code change? Any suggestions? How does the output change? Any suggestions? Okay, Sandeep is correct again, that star counter equal to 0, right? That is going to cause an issue because we are saying that this is CUDA malloc memory, which is accessible only on the device. So star counter equal to 0 is wrong in this case. Okay, although the rest of the code might still be okay. Well, actually, that is not okay as well because this part will not work because we are accessing that plus plus star counter. So that is another problem. Only this part is okay because print k is passing the counter and incrementing, etc. But fun should not access a variable which is allocated only on the GPU, right? Because it's a host function also. So that is another problem. Okay, good. What about this code? So now I have declared an int counter globally so that it is accessible to all the functions. Counter cannot be accessed on GPU, Abhishek says. Right? So this is a global variable, but global variable on the CPU, and therefore it cannot be accessed from, I mean, it can be accessed here, and then from print k, when you try to access this from the as a device function, then plus plus counter is accessing this, which is essentially not a valid variable on the GPU anyway. Right? This part is okay. In fact, since this is a host device function, we should not use the plus plus counter. So it, as you can imagine, it must be a variable which is either local to that function or passed as an argument, or it should be host alloc memory, which is accessible on both CPU and GPU. So that part is fine. So now what do you suggest? They should work. Okay, Soumik says that this is not in pinned memory. Okay. Abhishek says it's a variable declaration issue. Sandeep says, is there any problem in host device encounter? Okay. Okay. So usually when I teach this in the class at IIT Madras, usually students say that this works, right? So I'm surprised that you guys are suggesting that this will not work, and you are correct that it will not work because host device is allowed only for the functions. It's not allowed for the variables.
And also, it will have similar problem as the previous. I mean, like if you had to assume that even the declaration is fine. I mean, but in the previous program as well, the counter was for host, but was used in the GPU. I think the same setup is here as well, right? So that way, that also can be. I don't know.
No, we were thinking that maybe by suppose this would have been supported by CUDA, right?
Right.
Then things seem to be okay. So you are accessing it here, you are accessing it here, and all the places, since it is available on both CPU and GPU, maybe it is okay.
But then we should have an host alloc, right, for counter.
Well, host alloc is one way of doing it. Maybe internally, when we declare this, CUDA can take care of doing a host allocation, something like that. Although it doesn't happen, but I'm just contemplating.
Okay.
This could have been supported. So that is what my students usually feel in the class. Therefore, they say that this is okay. But yes, currently the case is that it's supported only, host device is supported only for functions. Sandeep says counter cannot be the same on same GPU and CPU. I think that is the reason for invalid declaration. Well, exactly in a similar manner as host alloc memory, right? So the CUDA language can say that whenever you declare a variable as host device, I'm going to do a host alloc of that particular variable. I have the type, so I can figure out the number of bytes required, and then just use that particular variable in the plus wherever I access this plus plus counter or counter equal to 0, etc. I might have to pass that as a parameter, which can be passed as a hidden parameter, right? So that is a translation problem, I mean, compiler problem, but it seems to be possible. I mean, if one needs to, if one wants to support it, it should be possible to be supported, is what I feel. Chinmay says consistency issues or too many syncs with CPU GPU. Yes, that is going to be there. But that is going to be there even with host alloc memory. And the same problems will arise. That is there. We are not saying that we'll support something better than host alloc memory. But yeah, this can get translated into a host alloc. It doesn't happen, but yeah. Okay, good. So, oh, by the way, when I said host device, a variable cannot be declared as a host variable, right? So, I mean, when I say host device, so variable can be declared as a device variable. Okay. So this actually creates a global variable on the GPU. So when I declare a variable as underscore underscore device underscore underscore, then it creates a global variable on the device which is accessible to all the GPU functions. And so now, is there a problem with this? Any suggestions? Race condition, okay. Problem with fun accessing GPU variable, okay. So where is the race condition, Sayan? That plus plus counter. But we are calling that fun with single variable, single thread, right? So we are calling print k as 1 1. So there is a single thread.
Maybe not for this case, but if we
But let's look at what Sandeep is suggesting, right? So we said that fun is host device function, and therefore whatever data it accesses should be accessible on both host and device. Right? Whereas the counter is actually a device only variable. So from our discussion, it should not be supported. This is where that exception part I was mentioning some time back comes into picture. That actually in this code, if you look at it, there is host is not really accessing the counter, right? So it's calling print k. Print k is a kernel which is calling fun, which is a host device function. It's using only the device part of it, and therefore that way this code is actually going to work. And therefore compiler says that it gives a warning and compiles the code. But anyway, this is something which you should not do. If you actually want it to be a device only function, then you don't create it as a host device. Right? So that is what we should do. All right. Any questions so far? Otherwise, we'll move to thrust now with that background. Actually, not thrust, right? We'll have to do something. Okay. Is there is fun call from main? Will there be runtime error? No, it will be a compile time. So the compiler is able to figure out that there is a CPU function. Yeah, so can we write a code to increment all the elements in an array? Call this code from the host as well as the device. I'll give you a few seconds and please try this out, and then we'll discuss. Right, so there is an array given, vector given, and you just want to increment all the elements in that array. Right, so just that particular increment function, you should be able to call from both CPU and GPU. That means that you need to mark it as host device, but I would like you to ensure that the array gets incremented. How will you write the code? Okay, any suggestions on how you will write this code? Or if you have written the code, you can also copy paste. Soumik has given the code. Error of I. Okay, call this function on GPU for some parts and call this function on hosting. Very good. That's good. Any other suggestions? Okay, so let's uncover this answer step by step, right? So one of the ways is that you can just have the for loop on the host in the host device function, which just increments it, and then call it from the kernel or call it from the CPU, right? Where the GPU function is getting called with a single thread. Right? So that is one possibility, in which case everything is completely sequential, both on the CPU as well as on the GPU. Okay. So another way is that, I mean, since this is sequential on the GPU, I would like to probably make it parallel on the GPU. So can you avoid that for loop in fun? So we can try that, right? So what we could do is essentially have that loop from the CPU, as Soumik was suggesting, and the dfun, which is the kernel, calls it with either an index or directly a pointer to that particular address, and that address, using that address, whatever pointer is being passed, we just increment that value. Right? So since this is based on thread id x.x, individual threads are pointing to individual elements, and that pointer gets passed to fun. Whereas in the context of a CPU, we need to pass it as an explicitly inside a loop. This is device centric, which is sequential on the CPU. If anyway, it is going to be sequential on the CPU, but the for loop now is moved to the host side, and the GPU part becomes parallel. Okay, any questions so far? Okay, the question is, what if I don't like the for loop in main but still want GPU parallel code? Is there a possibility of doing that? Right, so I don't want that loop on the inside the CPU, but I still want the code to be parallel. Any thoughts on that?
Sir, without that host device function, directly we can CUDA malloc, we can pass, we allocate one memory location in GPU, as well as we create array here and pass it at global weight with that function. Can we do that without that host device?
So then it will be GPU only function, right?
Yes.
No. We want it to be accessible. This code should be callable from both CPU and GPU.
Both. Okay.
Yeah. I mean, you can do it device only, and you can have a separate function call for CPU only function. That is possible. But reusing it is usually helpful in software engineering terms, because then if you make some changes at one place, it also gets reflected in the other. So, is there any suggestion on how to get this done if you don't want that for loop from the CPU? The reason is more kind of pragmatic in the sense that, or usability based, right? I just want that function call to be done. Just that function call should be done, like the way I am doing function call from the GPU, right? I don't want that loop to be utilized, because then I can just support it as an API. Shams, is there a way to know if I'm running on whether on CPU or GPU that can differentiate the function? That is one way. Right? So yes, so there is a way. For example, there is a CUDA arc hash define, which gets defined only in the GPU code. So using that hash if def, you will be able to write two different codes, and accordingly it should work. So that is one way. Any other suggestions? Okay, so it's not that I'm suggesting you to avoid the for loop altogether. I'm just saying that avoid the for loop from the CPU. So we can actually push it to the GPU, right? But still we want it to be parallel. I hope that can give you some hint. Right? So I'll show you the code. Oops, I don't have that slide. Okay, I have removed it. Maybe that is given as a homework exercise for you. But anyway, the hint is that you can have the loop on the in the host device function and call it appropriately from the different GPU threads, such that appropriate element is going to get incremented. Just that the loop length is also specified by the call. In case of a GPU, you will specify the loop length as one element, whereas in the context of when you call it from the CPU, the loop length is going to be all the n elements. So please think about it, try it out. You'll be able to get it. Okay, so let's come to thrust. So you would have seen by now, by trying out all these assignments, that the amount of library availability on GPU, right, inside CUDA is actually limited. Many of the functions are going to be not available on the GPU side, which are available on the CPU. Right? So when we are dealing with, for example, C++, STL, standard template library, turns out to be a very useful mechanism where it supports vectors, sets, maps, hash tables. All of these are different kinds of data structures, aggregate data structures, which are supported. And then associated with that are different algorithms. For example, you can do some sort of reduction, or you can do some sort of counting. And you can also define your own functors, right, in the context of STL. So something similar was thought about for CUDA programming, and thrust is an outcome of that effort. Thrust has evolved quite a bit, and these days people start using some library called as cub, which is similar to thrust, has some extra functions. But thrust works and is now embedded. Earlier it was not, but now embedded as part of CUDA installation itself. So you should have it available. Earlier we had to install it separately. So idea is that from the CPU, you are going to call an API, thrust API. Right? Thrust is a library. So you are going to call a thrust API, which will perform some operation. So if there is a large operation that I want to do, you are going to split it as multiple thrust API calls. And all these calls you will make from the CPU itself, so that you don't have to worry about whether even that code is running on the GPU or not. Right? That is the extent to which we would like this to be supported. Of course, that is not fully true. You need to tell whether this is running on the CPU or GPU. But more or less, you don't have to worry about, for example, the launch configuration, how many threads, how many thread blocks, etc. Whether it is resident or not, like we were discussing about the global barrier. So all of these are taken care of internally by thrust. Right? So let's see how that works out. So it doesn't support all the data structures. It supports, for example, vectors, right, and some associated transformations. Programmer is almost, I should not say fully oblivious, almost oblivious to where the code is executing, but the code remains the same across CPU and GPU, and internally it makes use of the host device functions, right? So that is the reason why we have to understand all these aspects. So let's look at a simple thrust based program, right? So for which you will require some headers to be included. For example, you might have to include thrust host vector and thrust device vector, right? And now we are getting into the C++ regime, which means that although you will be able to compile with NVCC, right, you can write a C++ code even on the host side. Okay, so that means that you can use this cout, cin, etc., and just include IO stream and compile with NVCC, and that should work. I'm going to declare a host vector which has storage for, let's say, 4 integers. How do I do that? I just say thrust : so thrust is a namespace. Host underscore. Those of you who are unaware of C++, ignore that. Just focus on the syntax. Ignore what namespace means. It's just a scope. So host vector of integer, right? So that means that I'm declaring an array of integers whose variable name is h and its size is 4. Okay. I can initialize individual elements. So when I'm doing h of 0, it's actually creating a local array on the CPU and assigning h of 0 similar to an array index, right? So this part seems to be okay. I mean, big deal about it. This we do all the time in STL or in C arrays as such. H.size returns the size of the vector, right? So that I can do. And I can also print the contents of that h. So I go over 0 to h.size -1 and print h of I. Right? So all this part seems to be very nice, and we know that it works on the CPU. Interestingly, exactly the same syntax is supported for the device vector. Right? So that is the power of thrust, that the programming becomes relatively easy. Right? So okay, by the way, there is a resize also. Now I'm going to do a copying of the host vector h to device vector d. The way I will do it currently with my current knowledge is that I'll do a CUDA mem copy from host to device, and that is going to give me all the contents of h into d as such. What we will do here is that we'll declare a variable device vector of int, right, instead of host vector, and I'll just do d equal to h. How does that work? Because there is operator overloading, right, supported in C++. So therefore, this d equal to h is going to invoke that assignment operator, which will take care of doing the CUDA mem copy, right? And how does it know how many elements to copy? Well, it has the size function. So internally, it is keeping track of the size, and it also knows the type, because the type is given as, I mean, type is anyway part of the declaration. So this seems interesting. Now, are there more things we can do? Yes, elements of D can be modified exactly the way you are modifying H. So you can say D of 0 equal to 99. Note that you are writing it from the host, right? So this whole code is in main, whereas the device vector is on the GPU, which you are even unaware of. You just only the declaration conveyed that there is something related to device. But otherwise, all the functionality is independent of whether it is on CPU or GPU. Right? And this gets very beautifully implemented using operators, operator overloading. In case somebody is interested, you can discuss with me offline. H and D are automatically deleted when the function returns. This gets taken care of using the usual destructor part, right? So that seems interesting. So there is some hope now that my productivity is going to be a little better with this thrust device vector. Are there more things we can do? Yes. Before that, are there any questions on this particular code or anything related to thrust? All right, so I'm going to now do some more functions with thrust. Okay, Shan has a question. Can you explain the difference between host vector and vector? So host vector is something which is supported by thrust. Our std vector is supported inside std namespace, right? So as a part of the STL. These two are not equivalent or even compatible, right? So we should not use vector and host vector interchangeably. It's a specific host vector which is implemented in thrust. In fact, not all the functionality of vector is supported in host vector. Most of the functions are there, like this resize and array index operator, etc. But not all the functions. I don't remember which functions are not supported, but some functions are nicely supported. For example, begin end, the iterators, those are supported for both host vector and vector. Ankit says, are the writes to the device vector happening on the GPU? Yes. Interestingly, the writes are happening on the GPU. So there is either a CUDA mem set or CUDA mem copy happening underneath, and that can be a problem, right? As you would have probably guessed by now. When I write d of 0 equal to something, d of 1 equal to something, each one is a separate CUDA mem. Right? If I had to copy from H to D, I would have directly copied using single CUDA mem copy. Right? So that is where the abstraction can hurt your performance, right? If you are not aware of what is happening under. So yes, there is a device-related operation happening whenever we assign a value or even read a value. When I say x equal to d of 5, there is a CUDA mem copy happening from device to host. And then getting copied into X. Abhishek says updates to D are by what threads, right? So that is left to the implementation of thrust, but in this case, since it's if D of I, then there is a single thread which can operate on this, or there may not be any threads also if it is not being invoked as a kernel. It could just be a CUDA mem copy call. But we will get into the threads as we get into these functions. So whenever we want to operate on multiple data items, then CUDA launches or the thrust launches a kernel which is going to make these operations parallel. Science says, what's the advantage of host vector over vector here? Well, the host vector and device vector are compatible, whereas the vector and device vector are not compatible. So if you want to do processing across CPU and GPU, we will have to use this vector. Okay, so we'll move ahead. So I'm going to use some functions. So I initialize all the 10 integers of a device vector to 1, right? So that can be specified as part of the constructor as an argument. So we said that I declare a variable of type thrust device vector of type integer d, which has 10 elements, and each one can be initialized to 1, right? It can also be done in a different way, which we'll see soon. Now I want to set the first 7 elements of a vector to 9. That can be done using this fill command, right? And similarly, fill command can be used to do this initialization also. So there is an iterator specified d.begin to d.begin plus 7. All of this is, again, that plus 7 is an overloaded function, right? To 9, the value 9. This value is, again, could be of arbitrary type depending upon the type that you specify here, right? So that's the interesting power of templates that comes into play. I want to initialize a host vector with the first 5 elements of D. Right? So I can do host vector H, which gets a range D dot begin to D dot begin plus 5. So the second element needs to be one past, this second iterator needs to be one past the element. Right? So when we say D dot end, it points to not the last element, but next to last element. So similarly, D dot begin plus 4 is actually the fifth element. So D dot begin plus 5 is one past that element. Okay. Any questions so far? Does this seem interesting? Does this seem to be reducing your pains while dealing with CUDA programming? And we'll get much higher level tomorrow when Pradeep teaches you a little bit of at the C++ level what all you can do with respect to parallelism itself. Right? So here we are at least using this data structure. Okay, setting the elements of H2 0, 1, 2, 3 as a sequence. Well, there is a sequence command. So thrust sequence, you give a range, and that is going to fill up the elements, right? So how many elements are there? Whatever you have created with. So for example, if there are 5 elements, it is going to get initialized to 0, 1, 2, 3, 4. Copy all the elements of H back to the beginning of D. You can do copy from D dot begin to H. Sorry, it's the reverse. Sorry about that. From H dot begin to H dot end, you start at D dot begin, and the number of elements is going to be whatever is the number of elements in H. Right. So this is going to also resize it automatically, by the way, because D dot begin might not have enough elements. Here it thankfully has 10 elements, and H has only 5. But even if it's not, it's going to have it's going to do the deallocation of the previous memory and allocation of the new memory, copy the elements appropriately. So the size is taken care of. Again, it has a lot of overhead because now you start thinking about how do I implement this when D does not have enough memory. You'll have to deallocate that memory using CUDA free, allocate a new memory and move it as a pointer. And in fact, you might have to even copy the old elements before CUDA free, because in this case, it's overwriting the elements, but it's overwriting only the first 5 elements. Right? So in general, you might start overwriting at arbitrary place. So you might have to also do a copying of the elements. I can do a printing, for example, like this, and that is going to be okay with respect to how you do it on the host as well as on the device. All right. Any questions so far? Okay, let me finish one small part and then we will take a break. Yeah, so this part is fine. This part, I mean, these are just some internal details which we already discussed. For example, when there is equal to, then there is CUDA memcopy. When there is initialization via the constructor, then there is an iterator. There is resizing happening automatically. I can do this, and there is CUDA memcopy involved. And then there is a transform function which is also computed. Right? So this thrust transform is mother of all the various transformations, where we can say that I'm going to transform it such that I take 2 sources, DSRC and DSRC2, and I implement a binary operator using these 2, and I start writing into the destination. So x equal to y plus z, where x, y, z are vectors. So that this DSRC is x, DSRC2 is y, and DDST is z, and sorry, x equal to y plus z we said. So this DSRC is y, DSRC2 is z, and DDST is x, and this add func is the plus operator. Right. So this is a generic way of specifying, and this we do even in STD in the STL. So this add func could be user defined, and that is what we are essentially going to do next before we take a break. So some of the functions that thrust provides are find if some predicate is true, copy if, count if equal. So these are almost all the not almost, these are some of the functions which are also supported in the STL, the C++ STL. Yes, Vipin, go ahead.
Can you move back to previous slide?
Yeah.
Yeah, so in transform function, so like the size of DSRC2 should be greater than or equal to side of DSRC, right? And
That
those
is
should be
correct.
taken care by programmer.
Yes, you are right. So this is an important point, that the size of DSRC is specified here. That is Y, but size of Z is not specified. So it's going to expect that the number of elements of, the number of elements is going to be essentially end minus begin plus 1, end minus begin, end minus begin, right? So those many elements will be there. So those many elements should also be present in DSRC. Right? So that is correct, that we need to, it's the programmer's responsibility to ensure.
Okay, sure. Thank you.
Good observation. Any other questions here?
No, that's all. Thank you.
Okay, so some of these functions as supported. Right. So the algorithms that are supported by Thrust are dual implementations, and therefore those work on both host and device. Iterators as arguments must be on the same device, that is the DSRC, DSRC2, right, that we specify. These should be from the same device. Either both should be host vectors or both should be device vectors. A combination is disallowed, except for copy, which allows that combination to occur. Okay, so let's use that here. So we allocate 3. Okay, maybe what I'll do is I'll leave this for you to try it out, right? So allocate 3 device vectors with 10 elements, or maybe we'll do it. We'll have to do it together. Okay, so let me take a break here. I think we'll have to discuss this particular code. So we'll take a break. Maybe after 5-6 minutes, we'll sync up in the same meeting. Stop recording now.